like, oh, okay, no big deal, acid, I have that permanganate, I have that osmium tetroxide, ozone, whatever it is. Okay. Here's another molecule here, we add the periodate, it forms this here, and you get two of these molecules, because it's symmetric. Now the key is if you had this molecule, would you be able to go back to this? You're like, oh, where did this come from? It either came from the alkene or from the diol. Everybody okay with that? You'll get practice right there, that we just seen it maybe first time. But it's not that big of a deal. These reactions are not bad, but they're always going to be used in series with other reactions. Okay? You have to do some first step, and then the second step is this oxidation. Okay? There's not going to be, here's a molecule and just do an oxidation, that's just too easy. It's always going to be multi-step. Okay. Last question, here we go. Last one here. So we have this very easy symmetrical alkene. You're not going to be getting that on a midterm, right? There's going to be some stereochemistry with a methyl group sticking out here or something. This is just an example to test you on this oxidation business, the 3 different versions. So if I do ozone, what's going to happen to this? What am I going to get? Remember I taught you, just draw it again and just draw exactly the same way, but draw these little short ones over here. Draw the molecule exactly the same. Then you open it up. You count the carbons, 1, 2, 3, 4, 5, 6, and you're like, oh, okay, open up, and it's like 6 carbons. Okay. You're never going to be given this. You're always going to be given something like this. 1, 2, 3, 4, 5, 6. Right? That's the same as that. Equal. Everybody okay with that? Even though you see the linear form of it, you know that you can cyclize it, and it's probably a double bond there. But you're going to be given the linear form, so you have to be good at counting the carbons. So it's 6 carbons, therefore if I put it together, it's a cyclohexane ring. If it's 5 carbons, cyclopentane ring with a double bond in it, or something. Okay? There it is there. Everybody okay with the ozone? It oxidizes it up, but only to the first round. It cleaves it, but it goes up to the carbonyl. Permanganate, what does it do? To a double bond. It cleaves it, but it brings it all the way up to the highest oxidation level. So therefore, carboxylic acid. It goes to this, but it keeps on going all the way up to the acid. So I'm going to do the trick again. You draw exactly like how it's shown. That, OH, OH. Right? There used to be a double bond right there. I broke it and oxidized it all the way up to carboxylic acids. Then I can do the linear version. So then I count, right? 1, 2, 3, 4, 5, 6, okay. 1, 2, 3, 4, 5, 6. Okay, so I got the right carbons. I'm not making a mistake or anything.
For that one, what did it cleave off one of the carbons to make the CO2, or is that only if it's
That's one if it's terminal.
oh,
This is not terminal, this is secondary. Right? And what does the osmium tetroxide do? Does it cleave the double bond? Does not cleave the double bond. It just puts a cis diol across it. Okay. Don't forget these wedges, right? Right? You can attack from the top of the ring or the bottom of the ring. If the ring is flat in the screen, it can approach from where you guys are towards it, so it's going to form a wedge, or it can come from behind the screen, attack the double bond, going behind the screen, so it's a dash. So we can. And this is 50-50, right? You're not going to forget to draw the other one. Don't pick one, you'll get it wrong, the question. The question on the midterm or have to know that it can approach both sides equally, you're gonna form both. So this osmium tetroxide is pretty cool, but it forms a but it forms a diol, cis diol, but we don't really get any selectivity of what side it's gonna go on, unless, as I mentioned before, we put some directing group over here, like a wedge isopropyl group over here. So if there's a wedge isopropyl group over here, is it gonna bind? Now we're gonna get a major minor type of situation. Which one do you think it's gonna go for? Which one's major, which one's minor? One or two. Are they gonna be made equally? One or two. Which one do you think is gonna be made more? Two, right? It's obvious it's gonna come from behind. No big deal. The front, there's a big isopropyl group sticking towards you. That's harder for this osmium tetroxide to come from. It's gonna go behind. It's much easier access. Nothing's blocking this there. So this would be major, this would be minor. Okay. If it's 50-50, if I give you a number, that means equal, right? If it's 51-49, what does that mean? Someone gets elected and someone does not get elected, right? It's 50, like major, minor. Okay, it's a little bit more on this side and it's biased. Okay, there it is. Okay, now this is straightforward, easier part here. Now they're just introducing some stereochemistry in here, but we already know this. Okay, we've already done questions on this. Here's a terminal alkene. You add H2O, acid catalysis. So before we were just talking about oxidations. Now we're not talking about oxidations anymore. We're just adding acid across a double bond. You know the double bond, is it a nucleophile or electrophile? It's a nucleophile. H plus is the electrophile. The nucleophile attacks the electrophile. Okay. The double bond usually is the nucleophile. It attacks something else. We have to activate it. Okay. It has the electron density. It's attacking something that does not have electron density. There's a delta plus somewhere over here, some other molecule. So we add this. Everyone knows what's going to happen. It's going to pick up a proton. The carbocation is going to end up in the secondary carbon, correct? Yes, secondary carbon. So therefore, you're going to get the OH in that position. Now there's 4